So there are two different things you can be asked to do with these trigonometric identities. The first thing that we've been working on is just simplifying. So when you're simplifying, you're just given one expression, no equal sign, and you're just asked to rewrite it until it's in simpler form. Sometimes though, it's hard to say what makes something simple, and it's hard to define and know when you've gotten the right answer. The other thing you could be asked to do, which is what we're going to do in this unit, as opposed to what we did in the previous unit, is proving the identity. So in that case, I tell you, or you're told, what the expression is equal. Okay, so we're told that this expression is equal to this expression. It's true all the time. And our task is to manipulate the sides so that they are identical, so they look the same. So you go about that in pretty much exactly the same way. Now, your task is to try and prove that they are equal. So you're trying to show that they are equal. So you cannot assume that they are equal. That means you can't use any of the properties of equality. So you can't minus 1 from both sides. You can only minus 1 if they're equal and we're not sure. A good way to think about these, you won't see this notation, it's just a notation I like to use, is we're saying to ourselves, is it equal? We're trying to show that it's equal. We don't know for sure right now. So this isn't necessarily a true equal sign until we're finished, until we've proven that it works all the time. Once we know that it works all the time, then we could use the properties of equality. The best way to go about these is to pick the side that looks more complicated, that looks like there's something you could do. So for example, here, sine x plus 1. I could replace sine with some other things, but there's not really much I could do right here. If this had been a sine squared, I could think about the fundamental Pythagorean identity, but since it's just a sine, there's not much I could do. Whereas on this side, I'm multiplying, so I could use the distributive property. Also, tangent and cotangent both have ratio identities that I can put into terms of sine and cosine. So I'm going to pick this side. There's just more happening here and more things I can try. Now, sometimes we'll pick a side, we'll try some things, and we won't get anywhere. And in that case, maybe we'll just have to start again and try the other side. While you are working from home, make sure you're showing me those attempts. So if you try something and it doesn't work, you should still submit that as part of your work so I can see what you were thinking and we can talk about it. Okay, so when I go about this one, I'm going to use the distributive property. So I'm going to multiply tan x times cosine x and tan x times cotangent x. So remember, if you were typing this on Desmos, you would need to write tan x cosine x in parentheses and tan x cotangent x in parentheses so that you can check your work later. We're saying that this is equal to sine x plus 1. I'm running out of room right here, but the justification, as I said already, would be the distributive property. I use the distributive property to go from one step to the next. Now, a good tip that I think I've already mentioned is to change everything to sine and cosine. So, tangent, while tangent is equal to 1 over cotangent, I'm going to change it here to sine over cosine because then things are more likely to go together and simplify. Similarly, I'm going to change this tangent and this cotangent. There's a couple different things I could do here. For our purposes, I'm going to change it to sine and cosine just because that's a really good strategy. However, there's other ways, and maybe you've already seen them, and maybe not, that you could simplify the tangent and the cotangent. So I'm going to change tangent x to sine x over cosine x. And really, I say change it, but I'm not changing anything. These two things are equal to each other, so I'm just substituting. Since now I have fractions going on, I'm going to write cosine x over 1, just because later on it's going to help me to simplify it. Then tangent x, again, you could use a reciprocal identity here. There's very rarely one way to solve these. There's usually multiple ways. I'm going to make tan x sine x over cosine x, and cotangent x cosine x over sine x. And I'm still claiming that this is equal to sine x plus 1. But remember, I don't know for sure. I'm still trying to figure that out. Now, again, I don't have space here to justify, but my justification in this step is that I used the ratio identities. So I didn't change anything. I just replaced it with what it was equal to. The next thing that I'm going to do here, and notice maybe should have mentioned this earlier, but notice there's 2 terms being added here, and now I have 2 terms being added here. So I know I'm on the right track because this is what I'm headed for. So now I'm just going to use my multiplication algorithm. I'm going to multiply my fraction straight across. So I'll have sine x times cosine x over cosine x plus sine x times cosine x over cosine x times sine x. And I'm still claiming that that should wind up being equal to sine x plus 1. Notice I haven't really done anything to this side, just sticking to one side, which is how you should do these. Now, maybe you noticed this in the previous step. Maybe you're noticing it now. Again, my justification here is just the property of the algorithm for multiplying. So I just multiplied using my fraction algorithm. So now I have some 1s. All right, so cosine x divided by cosine x is going to make 1. Sine x divided by sine x is going to make 1, and cosine x divided by cosine x is going to make 1. All right, so now what remains here in this step, now that I've made 1, I'm just left with sine x. And now that I've made 1 over 1 here, I'm just left with 1, which is equal to sine x plus 1. So I did it. Generally, we end a proof like this with the initials Q, E, D, which in Latin, can't remember off the top of my head what it means, but it means that I'm finished. I've done everything I need to do. Another way you can end it is with a filled in box, which again says that everything I write after this is no longer part of my proof.